Okay, let's dive into this. Today, we're putting on our code detective hats to examine a pretty fascinating case of hidden inefficiencies in Haskell string processing. This explainer is based on a really great piece from developer Ang, specifically from part 147 of their Notes-on-Haskell-Programming. They noticed something in their code that, honestly, a lot of us would totally overlook. So we're going to jump right in and see how just a few tiny tweaks can dramatically improve your performance.
Right off the bat, developer Ang captured a feeling that I think we all know a little too well. They wrote, "It took a while to spot the repetition." I mean, if you've ever stared at a block of your own code for hours, thinking it looks perfectly fine, only to realize later that it's secretly doing like double the work it needs to, yeah, you know exactly how this feels. It's just incredibly relatable. Even super experienced developers can have these performance bottlenecks hiding right in plain sight, just waiting to be uncovered.
So here is the scene of the crime. We've got a function called summarize. Its type signature is pretty straightforward, right? It takes a piece of text as its input and outputs a string. On the surface, it's just a deceptively simple text summarizer. It looks like a completely standard, totally harmless functional programming function. But here's the big question I have for you. Why is this simple text summarizer secretly wasting resources? Take a second and really think about it. What could possibly be going wrong in a function that's basically just checking a string and formatting it? Well, the answer doesn't actually lie in what the function is outputting. It's all about exactly how it's evaluating the input behind the scenes. Let's zoom in on the original code snippet. When you look at it, there's a guard clause right at the top, length txt less than 20. To figure out if the text even needs summarization, the code obviously has to check its length first. Makes total sense, right? It evaluates the length of the text right out of the gate. But remember Ang's note about repetition? Lurking down in an otherwise block, probably hiding exactly where we just scrolled past it without a second thought, was a second length check. It was literally forcing the program to evaluate that exact same length txt all over again. To really understand why that's such a huge problem, we have to remember how Haskell actually handles text. Unlike languages like Python or JavaScript, where grabbing a string's length is often this lightning-fast O(1) property lookup, Haskell actually has to traverse the entire data structure. So, evaluating the exact same string length twice, that transforms a routine everyday check into a highly inefficient O(2n) operation. That means the computer is literally marching through every single character in your string twice. You are completely doubling the required work for absolutely zero gain. 2. That's the tragic number we're dealing with here. Those redundant calls to length txt meant the exact same calculation was running two completely separate times just for a single output. I mean, making the machine traverse and count the characters of the exact same string twice, that is a massive performance leak, and it's something we want to plug immediately. Now, what's really interesting about this slide is the direct, sleek contrast between the old, repetitive guards and the new logic. Instead of that clunky length txt less than or equal to 20, the refactored code simply uses a really swift len less than or equal to 20. We've successfully swapped out a heavy function call that forces a full recount for a simple, lightweight variable check. But you might be wondering, where exactly does that len variable come from? Well, the hero of our story here is the incredibly handy where clause. Now, while we all know it's used to bind variables at the end of a function, its real superpower in this specific context is acting as a built-in memory saver. It's basically a caching tool. It allows the text length to be calculated exactly once and then cached for use throughout the rest of the function. This totally prevents your program from having to reinvent the wheel, or in our case, repeatedly recount the exact same string. Looking at the exact syntax implementation straight from Ang's diff, you can see that by just adding where len equals length txt at the very bottom of the function, the code successfully captures that evaluated length value. It stores it securely right there in the variable len. So it calculates the string's length exactly one time, holds on to that number, and then the guard clauses up at the top can instantly check that stored value whenever they need it. No extra work required. So the crucial point is that by eliminating those redundant calls using the where clause, we bring the entire operation down to a much cleaner, much faster O(n) time complexity. The program now traverses the string to count the characters exactly once. That's it. We have effectively halved the processing time for the length evaluation part of this function. I mean, that is a massive, tangible win for such a tiny line of code. But wait, Ang actually didn't stop there. Let's pivot to the second clue in our code detective journey. There was another major redundancy targeted here, and it was duplicated unpack calls. In Haskell, unpacking text into a string requires real processing power.
and the original function was individually unpacking the start strings and the end strings completely separately. Once again, we run into our main villain, repetition. So let's walk step by step through the totally new logical flow that optimizes this string unpacking process. Step 1, you concatenate the start and end strings first, while they are both still in their original text format. Then, step 2, you unpack that single newly concatenated result just once. Think about it. By combining the pieces before unpacking them, rather than unpacking all the little pieces and then trying to glue them together, you drastically streamline the entire operation. It's just so much cleaner.
And this brilliantly illustrates Ang's final takeaway from these programming notes. They said, they're small changes, but definitely effective ones. It's incredibly satisfying to see how these micro-optimizations, like shifting a variable down to a where clause to cache a calculation or concatenating your text before you unpack it, can drastically tidy up functional programming code and genuinely, measurably boost its efficiency.
Which brings us to the end of our investigation today, but perhaps the very beginning of yours. Are there hidden O2N operations lurking in your codebase right now? I challenge you to take what we've unpacked in this explainer, go back to your own projects today, and become the code detective yourself. Check those guard clauses, look for those repeated calculations. You might just find your own highly effective, small changes just waiting to be made.